Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3. We'll present the segment from Mr.Edi Untoro and Unconventional Reservoir about Carbonate Reservoir. There is Adriyasah Alimuddin, our team, Charles Amos Ganwarin, Henderika Takarbobir, Igor Wimaranda, and Patrik Juhair Fauzan. Please listen and pay attention to our presentation.
The introduction, the goal of reservoir characteristic to describe spatial distribution of petrophysical parameters such as porosity, permeability, and saturasi. In the chapter 1, we show the porosity, permeability, and the saturasi are linked through porosize. And this chapter we will expand some simple porosize to porosize distribution, that is the spatial distribution of porosize within the rock, and show how porosize distribution can be linked to the rock fabric, Perlen log, core analysis, production data, pressure build-up, and tracer test provide quantitative measurement of petrophysical parameter in the city of wellbore, but they generally provide only one dimension spatial information. Therefore, wellbore data must be integrated with geological model to display the petrophysical property in three-dimensional space, and study that relate rock fabric to porosize distribution. And these two petrophysical property are quantification of geological model is in numerical term for input into computer simulator. Okay, next. Next, rock fabric petrophysical classification, such as classification of interparticle porous space and classification of fuggy porous space. Okay, the foundation of Lucia classification as well as of RCL classification in the concept the porosity distribution, that is the spatial distribution of porosize within the rock, control permeability and saturasi, that porosize distribution is related rock fabric, and in the order to relate carbonate rock fabric to porosize distribution is important to determine if the porous space belong to one of three major porous type classification: interparticle, spare foot, or touching foot. Each class has different type of porosize distribution in interconnection. As present to chapter 1, the process of interparticle pore of control by particle size and sorting, and by the volume of interparticle cement for the particle size and sorting. The interparticle pore size will be reduced in proportion to the volume of cement. The process of spare foot will vary depending upon original and can vary from larger to micro pore within gain. fabric petrophysical relationship. Limestone. We see a limestone rock fabric. Example of limestone rock fabric with little fogging. Little fogging pores space are illustration is figure 8 next slide. And in grainstone fabric, the pore size distribution is controlled by grain size and sorting and by the volume of intergrain cement, which of relate in the amount of interparticle porosity. And figure 8 example of non-fogging limestone rock fabric. Grain with some spare foot of space. Next, grain dominant packed stone, large grain dominant packed stone, mud domain packed stone, and next mud domain packed stone with some spare pore space, and wax stone with microporosity, and the last scanning electron microscope photo of microporosity in wax stone. Figure 5. This is a figure 8. And the addition of spare full porosity interparticle porosity alter petrophysical characteristic by altering the manner in which pore space is connection. This connection, all the pore space being connection at some level. Example of the spare full pore space are illustrated in figure 20. These spare full are not connection each other. They are connection only through and the particle pore space and through and the addition of spare full increase the total porosity and does not significantly increase permeability. This is by Lucy. And figure 91 is illustrate this particle. And permeability of moldy grainstone. This is moldy grainstone is less that will be expand if all the total porosity were in the particle and at constant porosity.
Example of touching pore space are illustrated in figure in the screen and have little relationship to rock fabric. Touching pucks can increase permeability well above what would be expected from the interparticle pore system. By Lucia, 1983. Illustrated this fact by comparing a plot of fracturing permeability versus fracturing porosity to the free petrophysical field. This graph shows that permeability in touching puck pore system cannot be characterized by rock fabric or petrophysical classes. Estimating the permeability of touching puck system is difficult because the pores are often larger than the wellbore. The best information about flow properties comes from production data. In general, core measurements are not meaningful because of the large size of most touching puck systems. The core analysis of the cavernous core from northern Michigan, like the figure 23A, report a permeability lower than 0.1 millidarcy, which is clearly not a useful value. However, the permeability of small touching puck fabric composed of microfractures and grain molds can be measured by routine methods. And touching pucks for types in the A core pore space in the Nigerian Reef, northern Michigan, and the image B as cavernous pore space in Miami Olyte, Florida. In image C, solution and large fracture with saddle dolomite, Allenburg, West Texas. And the image D is a solution in large fracture Permian West Texas, and the image E is a pastoral pore space Permian West Texas. Image F is microfractures connecting grains mold in the Wake Stone Cretaceous Qatar. And the last one is the image G is a microfracturing and collapse of a post-mold Permian West Texas. Okay, let's move to the slide 7. In this slide, there is a properties of carbonate sediment. Like we see in the screen, the initial process in the formations of a carbonate reservoirs is sedimentation. The carbonate sediments are commonly produced in shallow, warm oceans, either by direct precipitations of the seawater or biological extraction of calcium carbonate from seawater to form skeletal materials. The result is sediment composed of particles with a wide range of size, shapes, and mineralogy mixed together to form a multitude of texture, chemical compositions, and most important, the associated pore size distributions. Carbonate sediment can be divided into loose sediment and sediment bound together as a result of organic activity. Sediment can be organically bound by filamentous algae to form algae stromatolites, or by excrusting organisms such as the modern coralline alga Lithamium or Devonian stromatoporoid to form reef. The beading actions can be create large constructional activities, which result in high permeability sediment like the figure 1. And more commonly, carbonate sediments are composed of loose grain. The grain size of loose sediment is generally bimodal, being composed of a sand size or larger fraction and the mud size fractions. In general, sand size carbonate grains reflect the size of the calcareous skeleton of their calcified hard parts. Coral fragments, or for example, are typically bonded size particles, whereas shell materials is typically much smaller. Let's move to the slide 8, which is in the screen we can see sequence stratigraphic framework. The spatial distribution of petrophysical properties in carbonate sediment is controlled by distribution of the positional texture, which is best described in terms of chronostratigraphic sequence stratigraphic framework composed of high-frequency cycles, or we can say this HFC, high-frequency sequence or HFS, and composite sequence, Crins and Fitchens 1995. A HFC is a chronostratigraphic unit defined as the successions of genetically related texture beds or bed sets bounded by marine flooding surface and their correlative surface. A HFS is an unconformity bound series of HFC that show transgressions and progradations. You can see in the figure A, marine flooding events and associated unconformities are believed to be a result of stochastic sea level fluctuations, assuming a constant rate of subsidence. Each HFC begins with the flooding event produced by sea level rise, resulting in the transgressive retreating shoreline and an increase in space available for carbonate sediment to accumulate. And sea level rise followed by still sand, during which sediment partially or completely fill accommodation space. The still sand is followed by a sea level fall, reducing accommodation space and resulting in prograding regressive shoreline and transport of sediment from the shelf into a basin, as we can see in this screen. Okay, we have an example here, which is in the slide 9. This figure in the screen detail ASM detail mapping was done on the reservoir cycle window within the formation that is close analog for many San Andreas reservoir of the Permian Basin. The reservoir window is about 1 mile or 1.6 km long and 150 feet or 30 meter high. Various descriptions from numerous measure sections indicate 9 high-frequency cycles that can be mapped along the line of the outcrop. The cycles are predominantly asymmetric, upward shallowing cycle and typically begins with basal mudstone, followed by waxstone and mud-dominated backstone, grain-dominated backstone, grain and local of fenestral, or we can say it as a tidal flat cap. And we also see in this grain that is cycle 3 and 8 have tidal flat caps. Cycle 1, 2, 3, 7 and 9 are subtidal cycle with thick grainstone or grain-dominated backstone caps. And the cycle 4, 5 and 6 have thin grain-dominated backstone caps, a section's boundary at the contact between cycle 3 and 4. And between cycle 9 and overlying cycle that overlap the cycle 9 of exposure surface, the cycle 1 until 3 are prograding cycle of a lower high-stand system track, and the cycle 7 until 9 are prograding cycle of the upper high-stand system track.
Okay, next, a key question in mapping diagnetic effect is the degree of conformance between diagnetic product and deposition pattern. If the transport of material in and out the system is not a major factor in production the diagnetic product, the product will generally conform the depositional patterns. Whatever is the transport of ions in and out of the system by fluid flow is required for product the diagnetic product, then the diagnetic product may not conform to deposition patterns. In this case, knowledge of the hydrological system may be required to map to diagnetic product, including the source of the fluid, the direction of fluid flow, and the geochemical change the earth along flow path. Okay, next slide. Modified seawater is thought to be only adequate source of magnesium for the volume of dolomite absorbed in nature. However, a mechanism from driving large volume of modified seawater to carbonate that is required to convert a limestone into a dolomite. Models have been proposed to circulate that form of seawater track of carbonate. Number 1, hypersaline reflux flow. Number 2, mixing zone, and number 3, thermal. The mixing zone is focused on the mixing of deposit and marine along the margin of platform and under islands. Like the increase in port size result from the reorganization of port space during dolomitization. For example, 200 pm dolomite crystal will occupy space 1 not only by the less than 20 pm calcite or Also, the micropore spot between those crystals, thus then 200 pm dolomite crystal are both refreshing the calcite crystal and outclouding the micropore spot between the crystal. Because the dolomite crystal offers more space than pre-existing calcite crystal, calcium, magnesium, and carbonate must be transported to the seat of the growing dolomite crystal. There are two basic sources from the calcite, magnesium, and carbonate ions. Number one, dissolution of nearby carbonate crystal, and number two, regional groundwater. Their source of referred to be Murray as local and distant source. The dissolution of nearby carbonate production enter crystal porosity, whereas precipitation of dolomite from regional groundwater production dolomite cement.
Moving to the next slide, I will explain to all of you about dolomitization. The pattern of dolomitization will be controlled by the source, volume, and flow path of the dolomitizing water. For the hypersaline reflux model, the source of the dolomitizing water is the supratidal environment. The volume of dolomitizing water will be related to the history of the peritidal environment, and the flow path will be controlled by the permeability structure of the underlying limestones. If a small volume of hypersaline water is formed, only the tidal flat facies will be dolomitized. If large volume of dolomitizing water are produced, hundreds of meters underlying subtidal sediment can be dolomitized. Okay, moving to the next slide. Okay, the next slide is evaporite mineralization. Anhydrite or CaSO4 and gypsum are evaporite minerals commonly found in dolomite reservoirs. Halite is uncommon but may be found occluding pore space adjacent to salt beds. Gypsum is the common evaporite mineral found in modern sediments and at shallow depth, but modern anhydrite nodules and layers are found in the Thracial Coast Sabha, Butler 1969. Evaporitic tidal flat environments are a source of sulfate as well as magnesium-rich waters. Poikilotopic and nodular forms have little effect on reservoir properties. Bed evaporites are commonly found in tidal flat facies tract and from reservoir sills and barriers. Porphyrin anhydrite is commonly found in greenstone associated with thick tidal flat facies and can be mapped according to depositional patterns. This is more detail about evaporite mineralization. Halite is also found as a pore-filling evaporite mineral in carbonate reservoir associated with bed halite. Halite is very soluble and is easily dissolved out of subsurface samples during sample preparation. It is isotropic and clear under petrographic examination, making it difficult to identify in thin section. Impregnating the sample with blue plastic is very helpful in distinguishing halite from pore space. Four types of anhydrite are commonly found in dolomite reservoir. Poikilotopic anhydrite is found as large crystals of anhydrite with inclusions of dolomite and is often distributed randomly throughout the rock. Crystal formed by a combination of replacement and pore filling mechanism, and porosity is reduced in proportion to the amount of pore filling. Poikilotopic anhydrite is typically scattered and unevenly distributed. Therefore, between the crystals, the matrix maintains its original pore space distribution, and permeability and capillary properties are related more to pore size than to porosity and are only slightly modified by the formation of poikilotopic anhydride. Pore-filling anhydride is typically pervasive and reduce both porosity and pore size distribution of carbonate reservoir rock because it occludes intergrain, intercrystal, and fuggy pore space. Bedded anhydride is found in laterally continuous beds, a few inches to hundreds of thick, and is deposited out of hypersaline body of water as gypsum and later converted to anhydride. Beds of coalesced nodules are interrupted to have formed as a large gypsum crystals growing on the bottom of a hypersaline lake. Okay, the next slide is about limestone reservoirs. The three-dimensional spatial distribution of petrophysical properties is controlled by the spatial distribution of geologic process and the process that can be separated into depositional and diagenetic. In chapter 4, we discuss about depositional processes and focus on the origin of depositional texture. The relationship between porosity, permeability, and depositional texture, the vertical and lateral distribution of depositional texture related to the topography and then the current energy, biologic activity, and then aesthetically controlled activity. The fundamental of sequence stratigraphy, importance of chronostratigraphy surface, was emphasized as the fundamental element in constructing a geological framework within which petrophysically significant depositional texture can be systematically distributed. A key question in mapping diagenetic effect is the degree of conformance between diagenetic products and depositional patterns. If the transport of material in and out of the system is not major factor in producing the diagenetic product, the product will generally conform to the depositional patterns. However, if the transport of ions in and out of the system by fluid flow is required to produce the diagenetic product, then the diagenetic product may not conform to depositional patterns. In this case, knowledge of the hydrological system may be required to map the diagenetic products, including the source of the fluid and then the direction of fluid flow, and the last is the geochemical change that occur along the flow path. Maybe that's it about the limestone reservoirs, and moving to the next slide.
The process of cementation, compaction, and selective dissolution, compressive and diagenesis environment characterized by shallow marine diagenesis, shallow meteoric diagenesis that relate to local superficial exposures of soils and detailed taints, and simple barren is seawater groundwater. And calcium carbonate cementation. Calcium carbonate cementation occludes pore space and reduce pore size. Studies have shown typical texture to be expected from both bladed cements, aquarium or blackish pressure cements, synthetic scale cements, pendulous cements, mensured cements, and radial cements. And compaction effect are difficult to separate from cementation effect, but they both reduce size and porosity. And selective dissolution is the diagenetic process by which carbonate and evaporate minerals and decompose and remove it, thus creating and modifying pore space in reservoir rock. Effect on petrophysical properties distribution. The effect of shallow diagenesis and simple boreal diagenesis on petrophysical properties can usually be related to dysfunctional textures and boreal or geologic time. The Mrs. Chester gas reservoir on northwestern Oklahoma is an example of a plutocenic limestone reservoir in which the porosity is controlled by the positional phases and type of selected cement. Although this is a short study, in excellent sample of how the depositional instruments can be used to model reservoir properties when the deposition products are closely linked to depositional texture. The genetic history is relatively simple, being confined to completion and cementation. The reservoir section is composed of two upper-salt high-frequency cycles consisting of lower conditional Reservoir and an upper conditional grain dominant texture and gaseous phases. The rock fabrics are greenstone, grain dimension, flagstone, and wood-dimension limestone. The only pore type pipes in between the grains in some of the greenstones. Much of the pore space has been occulted by syntaxial and episode cement and compaction. Follow Cretaceous files of short brazil. Vertical stacking patterns from core depression of the Cretaceous of the Sanson Basin offshore Brazil. Core depression relieve the presence of greenstone cavities to high-frequency cycles that can be grown into high-frequency sequences based on cycle thickness and the distribution of monumented fabrics. The four geologic phases are grouped into the three basic rock fabrics, and each is divided into upper grain dominant layer and lower mud dominant layer. The example of limestone reservoir present above are all located on carbonate ramps. Major limestone reservoirs also occurred in step-shaped remitted carbonate platform, but attached and insulate highly productive upper deviation reef bollards are found in the Alberta Basin, Alberta, Canada. This built-up or isolated platform with several hundreds of feet in relief and up to 1,050 square miles in area and are excellent sample of remitted platform. In the past, the built-ups have been reverted to ash reefs. However, they are more correlated build-ups reminiscent from the terms reef to beaded stone faces. The margins have relative steep slopes into the basin and contaction beadstone reef faces characteristic of remitted platform. Many have been completely dominated. The Reservoir and Swallowset built-up are limestone, and production is controlled by the distribution of depositional phases. The deadwater built-up is the Unconventional 150 quarters mile. Production is local and the quarterly high conservative margin on the built-up. Cloven presents detailed description of this area. So this is a presentation from our group. Thank you so much.